Hi, everyone. My name is Alex Bajcz, and I am MASERC's new quantitative ecologist. I started in June, so this may be one of the first times some of you are seeing me. Who I am not is John Feeberg. John Feeberg and I were going to be splitting the duties on today's talk, but he got called away at the last minute for a family emergency, so I'm going to be doing the first half of the talk here today using his slides as well. So I apologize in advance. I'm going to do my best to present these slides as well as John would have. I know he would have preferred to be here in person to present them himself, but we'll just have to soldier on. So this presentation highlights work by our 5-member research team, which includes Doctors John Feeberg, Dan Larkin, and myself, as well as Sabby Berra and Wes Gleason, who are shown here. And to simplify a bit, our research is split into 2 modeling efforts in which we attempt to do the same things, but at 2 different scales on 2 different species. Overall, our effort is to try to develop models that can integrate data from multiple different data sources that can hopefully inform monitoring and management of invasives, as well as improve our understanding of why invasives are where they are, while accounting for several challenges that come about when trying to build models that do that. So this talk's to me sort of split into 2 halves. In the first half, we're going to be talking about the first sub-project, which was led by John and Sabby, where we developed a model for predicting how Eurasian water milfoil, or EWM, might spread between lakes in the state based on the characteristics of those different lakes. In the second sub-project, which was led by Wes and I, we developed a model for predicting how starry stonewort, or SSW, might spread within a lake based on the characteristics of different locations in those lakes. So 2 very similar models or modeling approaches operating on different species and at different scales. So to briefly remind us all as we move into the EWM half here, EWM is an aquatic plant that is native to Eurasia, broadly speaking, but is invasive here in North America, where it is unfortunately capable of causing major economic, ecological, and cultural harms. And actually, I should say the same could be said for starry stonewort, which I'll be discussing later on in this talk. The data for our EWM model that we were seeking to integrate came from 3 major sources, which I'll talk about on this slide. The first of these was the Minnesota DNR's own list of infested waterways, specifically from the period of 2007 to 2018. The second source was 3,000 plus point intercept aquatic plant surveys that were collected on a large number of Minnesota lakes throughout the state during that exact same time frame. And the third data source was data on how boaters were moving between pairs of lakes in the state, as gleaned from surveys conducted during watercraft inspections from 2014 to 2017. So to clarify very briefly and to highlight these data a little bit, a PI survey is a systematic documenting of what plants exist where in a lake and how abundant they are. So in this pic here, you can see that a grid has been sort of overlaid over top of this lake. And at each point in the grid, someone went out, threw a rake over the side of a boat, reeled that rake in, and then saw what plants came back on that rake head. And that's the kind of data we're talking about. So I'll talk more about these data and where they come from later on in this talk and also in the next one in the same room. So as you can see here, very different data gathered in different ways at different scales for different purposes by different people, but which we're trying to bring together into one model here. So this effort built actually on past work by other MASERC researchers. Thomas et al. Did a study that found that when you are trying to explain which lakes in the state are infested with EWM and which aren't, that the best explaining variable out of all of them for doing that is something called autocorrelation or clustering. Are you near another infested lake, basically, then you're likely to be infested too. That's not to say that there weren't other important variables, but this one is the biggest one. So we might ask, what's causing that clustering? Is that clustering about habitat suitability? Are similar lakes that EWM likes being in, do those just happen to be near each other? Or is it about where we're looking for EWM? Do we tend to look for EWM in lakes or near lakes that are already infested? Or is it about how EWM moves? Does it just spread in a clustered fashion, or is it some combination of the 3? The reason this matters is that if it is either of those last 2 things especially, assumptions we might make about risk from models like the one we're trying to build might be questionable if we're not accounting for those factors. So what we tried to do in our model is integrate 3 processes together: habitat suitability, spread mechanics, so how starry stoneware is moving around the state, or these biological processes, and then this observation process too, how it is that we're actually trying to track its movements or look at where it might be. So this is a complicated slide, but it's sort of a conceptual overview of the whole model and its different interconnected parts. And what John would want us to focus on here is that at its core, the model is trying to predict whether a lake is likely infested with EWM or not, whether we know about that infestation or not. And we assume a big part of that likelihood is how connected that lake is to other lakes. How many boats are coming into this lake from other lakes? So that's the yellow piece here. However, that infestation likelihood is also related to characteristics of the lake, such as its size and water clarity. And interestingly, we assume those things also factor into how boaters may use that lake. Maybe they prefer going to larger lakes, for example. So that's sort of like the biological processes bit of the model. And then there's the observation processes bit of the model. How are we looking to see whether a lake is infested or not? Because we might bias the data we're including if we're not accounting for that in some way. So maybe we're preferentially looking at lakes we already think are infested or that are high use or easy to get to. And that's something that we need to account for as well. So one key piece of the model, as I just noted, is that connectivity piece. How connected are lakes to each other by boaters moving between them? And the gist of this slide is that the model is using boater movement data that we already have to try to find patterns that explain why some pairs of lakes have many more boats connecting them each year than other pairs of lakes do. It then sort of extrapolates those patterns so that for any pairs of lakes in the state, we have an informed guess called U in the model for how many risky boaters or boaters in general are moving between those two lakes, which is a key piece in our model. Then, as you'll recall, a main goal of the model is to predict whether every lake is infested or not at a given moment, regardless of whether we knew it was infested at that point in time or not. So in 2007, the first year we have robust data for, the model starts making an initial prediction about which lakes are truly infested. And then in each subsequent year, it makes a guess about whether that lake will transition to infested if it isn't already. The probability of which we assume is a function of how many boats are coming into that lake, as well as variables such as lake suitability and time, which is what these first three assumptions are talking about here on this slide. As one final assumption, we assume that lakes never go backwards and become uninfested, which is both true to the reality as we know it, and it also really simplifies the math here, which you'll have to just take my word for. Okay, so John promised that there was going to be just one equation in here, and here it is. But don't panic. This is the equation that lies at the heart of our model. I said one of the key things we're trying to do is estimate that probability a lake is going to transition to infested. And that is what this eta or n looking thing is. That's the probability a lake is transitioning in a given year. Meanwhile, this psi or trident looking term here is related to how suitable that lake is for infestation. A higher suitability, a higher likelihood of transitioning. And then up here in the exponent is essentially just the numbers of boats coming in from risky places, right? The more dice you are rolling, the more likely you will roll snake eyes and you will become infested. And so this looks complicated, but this whole equation here is actually a famous probability rule that math folks would probably sort of immediately recognize. And this is how we're estimating that transition probability in the model. Last thing I'll mention is that observation piece, which I highlighted a couple of slides ago. Where are we more likely to find EWM, regardless of wherever it actually is, as a function of how it is that we're looking? So this is a major piece that we're incorporating into the model. And I'll just say here that to get this part of the model to do what we want it to do, we have to make an awful lot of assumptions, such as that sampling effort matters, how hard you are looking matters, that we're never mistaking other species for EWMs, which would give us false positives, and that infestations never go unreported if they are actually found, among other things. So what has our model taught us so far? Well, for one thing, it has confirmed something that we have long suspected, and that is that boater movements connecting lakes are really important. It's the large and most connected lakes that experience the highest risk of transitioning from year to year. Further, there are patterns in how lakes are connected to each other. It's lakes that are near each other and that have moderate water clarity, interestingly, that tend to be highly connected. And perhaps predictably, how we look for infestations also matters. We're more likely to discover EWM in lakes that are near cities or highways, so they're very accessible, and that are in more densely populated regions of the state. Plus, we can use our model and its results to do some really neat things, in my opinion, such as look at whether the probability an average lake is transitioning each year is going up or down over time. So that's what this left-hand side graph is sort of exploring. We can also estimate how many lakes were actually infested at a given year in the past, according to what the model thinks. That's kind of what's being shown over here on the right-hand side. This is the number of infested lakes the model think existed at each year in time. And I'll say that the actual known number of infested lakes is always at the bottom of these ranges, which suggests that we were probably unaware of some of the infestations that were occurring until a bit later on. There's like a lag before a lot of these infestations are caught. We can even estimate risk for individual lakes. And interestingly, one of the highest risk lakes in our data set to transition, at least as of 2018, was Lake Bemidji, which just recently became infested, I believe, in 2020. So it was after when our model sort of cuts off its viewpoint. So in some ways, you could say the model kind of saw that one coming, which I think is very interesting. So to briefly summarize here, this model is a success because it helps us understand not only how and why EWM is present in the lakes that it is present in, but it also helps us understand how we can adjust the ways we look for EWM moving forward, and also how we forecast what its next moves might be. So that's the first half of the talk, looking at between lakes and EWM. We'll now transition into this half, which looks at very much the same issues and challenges, but for starry stonewort now within lakes. And I want to frame what we're doing in this half of the talk within a paradox of invasive species monitoring that I think is exemplified by this famous quote from Tale of Two Cities: is the best of times is the worst of times, right? We ideally want to be monitoring for an invasive, especially hard and well early on when populations are small and thus they're still manageable. But that is unfortunately the hardest time to do it. I might not even know what I'm looking for yet or how to do it. Populations are small, maybe they're tucked away somewhere I wouldn't think to look, and maybe they're mixed in with a bunch of native plants because the spot that's good for one plant might be good for many plants. So you can see that this is a challenging thing to do well. Wouldn't it be nice if we had a tool to guide our early looking and help us know where we should be looking for a species, especially early on? So that's what we were seeking to build in this half of the project. Specifically, we were trying to build something that's called a within lake species occupancy model. And these are easier to explain in pictures than in words. So I want you to imagine that you have a lake and you know about some occupied spots in that lake. And you also know about some unoccupied spots in that lake, represented here by the red and yellow squares. And you know some things about what all of these spots are like. Maybe this one's deep and that one's mucky and so forth, right? The model will use those data to try to find patterns. Where does your invasive seem to like to be? And then it can make predictions about how likely any given spot might be to be occupied, which you could use to know then that I should be looking maybe here instead of there based on what we've observed in the past, which you can hopefully see would be useful. However, we wanted to add an additional dimension here that acknowledges a reality, and that is that some invasives are really sneaky. You can look for them in places you know where they are, and you can still not find them. Why? Could we predict this too, based on where we tend to have more or less success actually finding an invasive when we go looking for it? So we were trying to build a within lake occupancy detection model. It turns out, though, for reasons I'm not going to get into here, these are really hard models to build for aquatic invasive plants. So our model may never have been possible if not for the emergence, so to speak, of two key players in our story. The first of these is the invasive in question, which is starry stonewort, or SSW. It's been here in Minnesota since at least 2015. We think it's likely a major threat to our inland waterways. It's seemingly very sneaky in a bad way. It can be hard to find. And we're still relatively early in its invasion of the state. So it's kind of like an exemplar species we need to be monitoring for well right now. The second major player is Mike Verhoeven, which is a name and a face many of you will probably recognize. He's been a graduate student here in Macerk since 2014. And he's a really good one, as many of you know, and we're all very happy for him because he's going to be defending very soon. Most importantly, though, he's sneaky too, but in a good way. He knew that there were many groups throughout the state who were conducting point intercept aquatic plant surveys, which are those systematic efforts to document which plants are present where in lakes. And he saw the potential of these data to help us answer a lot of really thorny and difficult questions. So he began this massive collection effort back in 2014 to start pulling these data together, an effort which I will stress Macerk and me personally are taking over so that it will hopefully continue forever, even once Mike unfortunately leaves us. So thanks to Mike's and then Wes's efforts to gather these data together, we were able to amass a truly huge data set to build our model with. Thanks in particular to the many contributors throughout Minnesota and Wisconsin who contributed data. And I have a slide at the very end who thanks all of those people by name. This would not have happened without you. Instead of telling you, though, about our data set and our model in abstract here, I'd rather show you what the model is telling us so far and then talk about its composition as we go. So let's go ahead and just jump into our first major story here. And that is that our model lends support to an idea that we have long suspected, and that is starry stonewort is really sneaky. You can be looking hard for it in places where it is and still fail to detect it. In fact, our model estimated that the probability of detecting starry stonewort with a single rake throw at an occupied location is just 33% on average, so 1/3. Using basic probability rules, that means you'd need 8 tosses on average at every occupied location to detect starry stonewort at 95% of those, which is 8 times the current effort that is usually used. And that probability goes down even further if the spot you're talking about is densely occupied by other plants in general or other cariaceae in particular, which is kind of scary. So I'm going to put a map up here that gives you a sense of what the model is seeing to make that prediction. So each square in this map is where a sample was taken with a rake at Wind Lake in Wisconsin during the 2020 PI survey there. Blue squares are where we came up empty for starry. Red squares are where we came up positive for starry. However, it's actually really the purple squares I want you to be focusing on here. These are places where we came up empty for starry in this survey, but had found it in that exact same spot in at least one previous survey. So if we assume starry isn't actually disappearing from these places, these are maybe missed detections, right? Which hopefully gives you a sense of just how hard it is to monitor for this species, even in a lake that's pretty well infested, and why having a tool like ours could be a benefit. The second major story is also one that lends support to something we've long suspected, and that is starry seems to be very often found near motorized boat accesses. So to simplify what the model is telling us here a little bit, it seems to be bad to be near an axis, and it seems to be even worse to be near more than one. And to show you what the model is seeing here to reach that conclusion, I'm going to play you a little movie. It's maps just like we saw with the colored squares. It's a map or a movie of 4 lakes, Little Cedar, Silver, Moose, and Green, and it's maps of those lakes over time. What I want you to be focusing for and watching, focusing on as I do this, is where the red and purple squares end up. So I want you to be focusing on infested spots. I also want to draw your attention to locations of the yellow diamonds, which mark where boat accesses are on the lake edge. So I'll put this movie up and then I'll play it through a couple of times. Okay. As I let this play through again a couple of times, hopefully you're seeing the same pattern that the model is seeing, right? Infestations seem to be more often than not starting near axes and then spreading out from there. And I'm not saying that this pattern is this readily observable at every lake in our data set, but this is a pretty representative sample of the pattern that we're observing at many lakes and that the model is picking up on. And we can watch that video more in the Q&A if you'd like. The third major story is another interesting one that supports work that's results that have been found previously. And that is that starry seems to be preferentially found in areas of low depth and fetch. So it seems to like, quote unquote, shallow and less turbulent waters. And I have some relevant video here and text, but for the sake of time, I will skip them. However, if you would like me to come back to them in the Q&A, I'd absolutely do that for you. Instead, I want to highlight our fourth and final story. I mentioned earlier that species occupancy models can generate a probability that any given spot is occupied with the invasive in question, and I want to show you what that looks like. So I'm going to put up again a video of maps. This time it's from 3 lakes, Sylvia, Medicine, and Little Muskego. And in these maps, hotter colors are going to represent a higher predicted likelihood that starry stonewort is present there, with red squares being spots that we already know are occupied. So let me put this video up and then play it through a couple of times for you. All right. What I hope you are seeing as you continue to watch the video is that the model is assigning higher probabilities near axes, along shorelines, and in other areas of low fetch and depth. And it's also assigning higher values near spots that we already know are occupied, suggesting that the model is picking up on real patterns in the data about where starry stonewort really is. So you can kind of see that, especially, say, in Little Muskego here along the left-hand side. What I think is particularly exciting about this is we theoretically could do this for any spot in any lake, not just the lakes that we use to build our model, and not just at lakes we know are already infested. The catch there is that we would have to have the same variable data to be able to do that, which is, I think, another key reason we need to keep collecting these PI survey data, because they're the data that made this model in its current form possible. So this last slide highlights some self-identified limitations of our model, which you can read over here on the left-hand side. I want to instead close by highlighting 3 new questions that our model has raised for us that we think need some further investigation. The first relates to this pattern of starry stonewort being found preferentially near axes. What we might wonder is this a crime of opportunity? That's just where starry gets introduced to lakes, but it's not actually where it likes to be best. Or is it a crime of passion? There's actually something that starry likes about the typical conditions that are found near axes, such as maybe regular disturbance. And we dug into this a little bit in our data, and those explorations actually came back inconclusive. So there seems to be some work to be done there. Second, and I actually kind of mentioned this in the previous talk that occurred in this room, it was also clear to us that axes are by no means created equal in terms of risk. Starry may be very abundant near some and not abundant at all near others. So what are those factors that allow starry stonewort to thrive near some axes but not around other axes? That seems an important question. And then third, what are all those factors that influence that detection probability, that 33% I mentioned earlier, right? Our model probably only scratched the surface on answering that question, since it wasn't the focus of our research. So these seem to be significant knowledge gaps to us that we could prioritize in future work. All right, I said earlier, I would provide a specific thanks to everyone who contributed data to this project. So I hope I got everybody on here. Thank you so much. This work would not have been possible without you, and I hope you will continue to support our work well into the future. And then, of course, thank you to all of our funding agencies as well. And that concludes my slide, so I'd be happy to take questions at this time.
Thank you very much, Alex. That was super interesting. So people, I hope you will put your questions into the Q&A. To start off, we've got a comment and a question from Kevin Farnham, who, if you folks don't know Kevin, he is at Lake Coronis, which we kind of consider ground zero for starry stonewort. Important note from Kevin, and thank you for this clarification. We should all be careful to say that starry stonewort was recognized in 2015, but it was likely there for a fair amount longer, because he notes that it was 250 acres when it was first found. So thanks for that note. The question from Kevin is, so the probability of finding starry stonewort in sampling may also depend on if you're sampling to find it or not to find it. And he says micro sampling has identified this. Can you comment on that?
Yes, thank you for the clarification. I did try to imply at least that we only knew about it from 2015, but you're right, it's probably been here quite a bit longer, and I appreciate that clarification. As for your probability of finding it, depending upon how you were looking for it or whether you're specifically looking for it or not, absolutely does matter. And I know that this is something that my research colleague Wes Gleason was looking into specifically. And one of the interesting things about our data set is because it's PI survey data, which are just trying to account for all the different plants that might exist at a spot, it kind of hopefully washes out a little bit of that whether you're looking for starry or not kind of aspect. But certainly if you were specifically looking for starry, that might increase your odds. I don't have more to say about that. I think it absolutely matters. And I think one thing I would say personally is it seems like something we need to investigate specifically. Here, we're kind of almost investigating it or estimating it a little more ancillarily. I don't know if Dan, my colleague on the project, has more to add on that.
Yeah, thanks, Alex. Yeah, one of the things that Wes did that is not data that was presented today is he looked at if you sample more intensively. So instead of, he did PI surveys on starry infested lakes, and instead of just doing a single point, he did 4 points at each location. And so that's one of the things we'll be looking at is kind of having that more intensive sampling. What does that do in terms of that ability to detect that it's there that Alex was referring to?
We have one more question so far. And Alex, were you going to put that animation back up on the screen during the Q&A?
Which animation would you like me to put up?
The one that showed the 3 different lakes and the public and private accesses.
Oh, the public and private accesses. Okay, yes, I can certainly put this one.
Yes.
Okay. Yep.
Okay, question from Nancy. Do you have a model of a lake that uses the AIS sentries and a professional to augment screens?
Nancy, I would encourage you to throw a follow-up in there if I'm not answering your question correctly. But what I'm hearing here is how much are we incorporating about what we know is going on at the lake and how the data were collected? And the answer is we don't. We don't have anything in the model about whether or not interventions are happening at these lakes, especially at the accesses. We don't have information in here about whether the lake is being treated or not. We don't necessarily incorporate any information about who the surveyors were or what their purpose was with how they were collecting the data. All of those things would certainly matter. What we're hoping here is that we're detecting a signal through all of that variance. But are those important factors? I think certainly they are. But I wouldn't, unfortunately, know the specific answer to the question you're asking here, I don't think. Maybe Dan does, but I'm not sure.
Yeah. In this case, for this particular analysis that Alex presented, we are just incorporating point intercept survey data because it is something that was uniformly collected, and that we had data from Wisconsin and Minnesota. Again, I mentioned that, the thing with trying more intensive PI sampling, and then another thing connected to that piece was also looking at different rake tosses. So, in Starry Trek and other kind of early detection efforts, we rely on doing rake tosses from an access. So we also we resampled all the public accesses on all lakes in Minnesota known to have starry stonewort to test whether or not we'd find them by doing a Starry Trek style sampling. So I know I'm not directly answering your question, but in the broader project, we are bringing in some other types of surveillance. But for this particular effort that Alex is presenting, it's just relying on the point intercept survey data.
Cool. Oh, I like this next question. So is the goal ultimately to build a user interface similar to AIS Explorer to aid in detection? I'm guessing they're referring to the kind of our surveillance tab. And does MASERC have a point intercept training they plan to offer similarly to the AIS detectors training, or perhaps including it?
Yeah, this is a really good question. So let me start out by saying I think a visual or interactive dashboard of the kind MACERC is already working to develop, which I'll talk about in my next talk with Meg, makes sense to me. I'm not aware of any specific plans to do that. However, if there is an interest, I think where there is a will, there is a way. So it's good to get that kind of feedback. I will stress that the data set we're talking about here is immense on the level of these kinds of models, but it's still small in the relative scale of things. There's only 23 lakes in here. So in terms of like being able to broadly explore what this might tell us about within lake risk at the, across the state or across both states in terms of Starry Stone, we're not there because we just don't have the data yet. As for trainings, I am not aware. I'd have to defer that question to Meg. I will say, though, that the goal of this model is not to say, oh, we should be PI surveying somehow differently. I think that question earlier that said, it matters what you're looking for and how. What's nice about this data is that it was not necessarily specifically collected for this purpose. So it didn't necessarily have some of the biases that might have otherwise occurred in there. So I don't think we'd be advocating in some way for a different way of PI surveying, but perhaps this could still inform how we're monitoring for Starry Stone when that's specifically what we're looking for.
And I could take a stab at the training question, and then if Meg has anything to add as well. So in our AIS extension program, early on, we were envisioning kind of more of a citizen science systematic monitoring approach. And we piloted that and found that that was just a real high kind of barrier to entry for people who don't do this professionally. These are really intensive, time consuming surveys. And so we shifted course on that. So we do, however, there are resources available and some, nice documents that have been produced by the Minnesota DNR on kind of best practices for point intercept surveys. And I think it's something that's a real strength of lake monitoring is that we have a lot of different people essentially implementing the same method, which enables these types of multi-lake overtime analyses.
To whoever sent that email, it's showing up as anonymous on my screen, but please drop us an email, me and or Alex or Dan, to continue to brainstorm. I'm personally intrigued, and I think if this project developed to where we could have a wider set of lakes with that sort of lake level predictions of the best places, better places to search, and if people were interested in that, I'm intrigued to have those discussions. So let's stay in touch.
Yeah, and if I could jump back in there, so we will be using this type of approach in upcoming research. So kind of maybe a beta version of that possible future of having a dashboard like AIS Explorer. So we will be using it in at least one research project to sort of guide our search effort for more Starry Stone work in lakes.
Yeah. Okay. Next question comes from Doug Jensen, now with the Minnesota DNR. Community science monitoring has been steadily increasing over the past 30 years. Does the model account for the increased level of effort, both in the number of locations within water bodies searched and the number of water bodies? It's of Doug's opinion that reports of sightings are being reported by the public much sooner than in the past, perhaps even shortened by half for AIS such as zebra mussels.
So I think there's a couple of things in here, and I apologize in advance if I'm not quite answering the thrust of your question, but let me clarify a couple of things. There's no actual citizen science or community science data in here. These are all coming from, I guess we'll call them quote unquote professional PI surveys that were done. But the idea with the larger project here is to develop a modeling framework that you would be able to incorporate data coming from sources like that in the future in a way that accounts for the different ways that those data are being gathered. And I talked about that a lot in the first half of the talk because that was an explicit goal with sort of John and Savvy's half of the project here, because at their scale, they have that data. And here we didn't necessarily have that. I will also say that I think this gets at maybe a part of your question, but one of the variables in our model is how many times were you surveying and how long has it been since infestation was first known to have occurred at that lake. So there is an explicit incorporation of time and potentially the increase in effort over time. But the nice thing, in a way, is that the way these PI surveys are designed, they're meant to sort of fully encapsulate the whole lake surface every time the study is done. So there shouldn't be wild variations in effort from year to year in that way, unless multiple surveys were done at the same lake in the same year.
And I will just add, for the Eurasian water milfoil piece, as Alex mentioned, that does, the DNR infested waters list is part of that. So what you're talking about, Doug, of, you know, kind of more rapid detection does come into play there.
Okay, the next sort of a comment, maybe Dan or Alex might just want to respond to this. So it's coming from someone at Grand Lake, and for listeners not familiar with Grand Lake, this is a lake that where starry stonewort was discovered, I believe, in a Starry's Trek survey, 2017-ish. Grand Lake is a little bit southwest of St. Cloud. It was a very small infestation, and they've been aggressively managing it. James says that they do 6 full lake surveys each summer for the last 6 years, specifically looking for starry to see if make sure it hasn't spread from the access, and they do 4 hand pulls every summer in the access area, and so far it has not been detected. So that's wonderful news. Any response or comment to that?
I will comment to say that Grand Lake is one of, I think, 5 lakes in our data set out of 23 where we have PI survey data that was conducted after starry stonewort was detected in a lake, but that starry stonewort is not successfully detected at any point in the lake during those surveys. And we included those data on purpose as almost like negative controls. We know these lakes are infested. We know starry is there. You're not detecting it, though, when you're looking at it in a PI survey context. And we thought that was important information to include. And I think it's another thing that the model might be seeing when it's saying, oh, detecting this can be pretty tricky.
Yeah, that's a good point by Alex, and thanks for that comment, James. Yeah, and that also highlights, you know, the role of management, and that, you know, there is management happening in a lot of these lakes that could be slowing the spread. I think I'm going to use this just sort of as to say something tangential that is probably already clear from this presentation, but I think that the accesses piece, you know, that's something I've wondered about for a long time. So it's exciting to see these results, because we sort of always, you know, starry stonewort is so often found near accesses. And there's always this question of, is that just because that's where it's easy to look for it? Or is there something about accesses, you know, the opportunity to be introduced and then prop wash and disturbance that might make for suitable habitat? And I think something that's nice about these results is to see that, no, it's not just that those are easy places to search from, but that there is this sort of association. And you see that Grand Lake is an example of that, where, you know, you have the small infestation right by the access and nowhere else.
Great, thanks, Dan. So one last question so far from Tom Hubbard. Your presentation started with proximity to infested lakes and how it increases the odds of AIS spread. He notes that it doesn't seem like starry stonewort seems to be spread to lakes farther away. In other words, we don't have clusters of lakes with starry stonewort.
Yeah, I'm not sure if I'm totally understanding the question here, but yeah, it doesn't seem like there's a strong spatial pattern yet in which lakes get infested with starry stonewort, but I will caution you that that's based on a pretty small sample to be detecting such patterns. I will say that, like, in our data set, there's only 8 lakes from Minnesota. There's more in Wisconsin because we have 23 lakes total, but we don't have boater movement data in Wisconsin, at least not in the same forms that we have for Minnesota. So looking at those connections between lakes would be more difficult. And at least in the context of Minnesota, 8 is just not a big enough sample size to find those kinds of patterns in clustering. So it's possible that, yes, clustering doesn't play a role, but maybe it does, and we just aren't aware of that yet. And I think that's something that will maybe emerge as more lakes hopefully don't become infested, but might. But that's just my speculation.
Yeah, I'll interject here. I disagree. So for Minnesota, at least, we do see some pretty strong spatial clustering of essentially having two main clusters of starry stonework in the state that are sort of one in central Minnesota and then one in northern Minnesota. So it does seem pretty patchy in its distribution. But what Alex, mentioned, so we have 8 lakes. That's obviously less than the number of lakes in Minnesota that have starry stonework, but this is the lakes for which we had this type of PI data that we could use in this analysis.
Yeah, thank you, Dan. There was a question in the Q&A that I accidentally dismissed, so I'm sorry about that, but I was asking if I could show the maps or the video that I hadn't already shown, I think. So hopefully this is what the person was looking to see, is the movies I've got related to depth and fetch. And you'll just be able to see here basically that where they're both large, it seems to be bad for starry. Where they're both small, that seems to be great for starry. When only one or the other is low, it's sort of more medium. I'm not saying this pattern is this evident at every lake, but I think this is a good representative sample of 4 lakes that is showing the habitat suitability sort of variables here.